So, types of reactions and balancing equations. Now this is, I think, the PowerPoint for chapter 3. Isn't it? Okay. It's a long PowerPoint, and it's going to be a lesson that takes many, many days. So if you are a lazy student like me, right, I don't want to have to write all this stuff down, make sure you print these out in notes version and then use them as you're in class, or if you watch the videos I record, I'll put them online for you. So if you have the notes with you, that makes things a lot easier. All right. The reason that we balance equations is due to the law of conservation of mass, which says matter can't be created or destroyed, right? You can't create something out of nothing. When a chemical reaction occurs, the atoms and the molecules change places, basically, is what they're doing. Sometimes they get bigger or smaller because they gain or lose electrons. But basically what happens is bonds are broken, which costs energy, and then bonds are made, which gives energy back. Chemical equations are representative of what's going on a microscopic level. Remember when I started class, I said there's really 3 ways I like to talk about chemistry. The symbolic, which is what most teachers tend to talk about. The microscopic, which is what you can't see, which is actually sometimes more important. And the macroscopic, which ties together what kind of expectations are you going to see when you are in the lab and you see something happening in a beaker, what it is that you're looking at and what you're looking for, right? So if we talk about chemical equations, here's a good microscopic representation of atoms and molecules rearranging. So you can see there's 4 white ones on this side, and there's 4 white ones on that side. 4 red ones, 1, 2, 3, 4 red ones. So there's quite a bit of comparison. Now if we want to add the symbolic to the microscopic representation, the symbolic says that first molecule is a molecule of CH4. Does anybody know what CH4 is? It's a gas. Somebody said it. Methane. Good, good. Yes, that's methane gas. When you burn methane gas in the presence of oxygen, you produce carbon dioxide gas and water. Believe it or not. Yes, you make water. So what that's showing you is that you have 1 molecule of methane there pictured. You have 2 molecules of oxygen because they're diatomic, which makes 1 molecule of CO2 and 2 molecules of water. So looking at those things, you should realize that the numbers are on each side are the exact same. Reactants are on the left side, products are on the right side. And then you always put the states of matter. Solid, liquid, or gas. Solid is just like the G's are up there, except a little s. If it's liquid, you put a cursive L in parentheses. If it's a gas, you put a lowercase g in parentheses as a subscript next to the symbolic formula for the compound. That's nomenclature up there. If it's an aqueous solution, what's an aqueous solution? That's probably a vocab word. Yes?
I know it has to do usually with acids.
Acids are generally aqueous solutions. That's true. It doesn't have to be an acid, though, to be an aqueous solution. Acids are generally aqueous solutions, but what else could be an aqueous? Water is anything you dissolve in water is called an aqueous solution. So you could take most ionic substances, and remember, ionic substances are metal, non-metal combinations. When you put most ionic substances into water, it dissolves. And so that's why we call it an aqueous solution, because in this class, inorganic chemistry, we spend a lot of time talking about inorganic stuff like aqueous solutions.
So would we label
It would be a little AQ in parentheses.
I understand that, but we have water. Would we label that as aqueous or as liquid?
No, if you're talking about pure water, it's just an L. Good question. Good question.
What is the distinction? Aqueous and liquid?
AQ means that you're starting out with something that you have made a homogeneous mixture of, that you have put often an ionic substance into water, and what happens is the ions in the ionic substance break apart. The pull of the water molecules breaks them apart, which we're going to talk about in a little bit. But that's an aqueous solution, where water is often depicted in acid-base reactions because one of the products is water, or in combustion reactions, one of the products is water. You put L because it's a pure substance being produced. It may still be taking place in an aqueous solution.
So liquid's a
Pure substance.
product?
Liquids could be a reactant or a product.
Okay.
Because you could have, for example, you could have liquid hydrogen. And you could have reactions with liquid hydrogen. Good questions. All right, the subscripts represent the number of atoms in each molecule, like H2O means there's two H's and one O. And the coefficients tell you how many of those pieces are taking place in that particular reaction. Now, here's a crucial piece of information I want you to remember the rest of this course. A chemical reaction is like a recipe. One of the ways that chemistry teachers help their students understand what's going on a microscopic level and stuff you can't see is to bring in everyday examples of stuff you do have experience with. Everybody's cooked something according to a recipe, right? All right, so if you have a recipe for something, for example, here, it takes 1 cup of sugar and 2 eggs to make a cake. Except instead of 1 cup of sugar and 2 eggs, we're talking about 1 methane and 2 oxygen molecules. So that's your recipe. If you said, I have 10 of these CH4s, how many O2s would I need to use up all 10 of the CH4s? 20. Okay? So your recipe tells you what you need to bake 1 cake. But you hardly ever bake 1 cake in chemistry. How hard would it be to get 1 methane molecule and 2 oxygen molecules together in the same group? Probably pretty difficult, right? So we talk about larger quantities. And so that's what we're going to be doing with the calculations in this unit, is figuring out the quantities of reactants and products. And so I want you to think about a chemical equation like a recipe. So I'm going to use that metaphor continually throughout the class. All right, I'm not going to go into the individual types of reactions according to the PowerPoint, but here's what the PowerPoint is good for. I'm going to switch over to the Ladybug now because it works better if I can show examples with chemical equations. I'm going to suggest to all of you that you go through, you read the PowerPoint, and if you see that I've created some links that are there, and I don't do it just for fun, I do because those are important links that help you understand the microscopic and the macroscopic of chemical reactions, because generally what we're asking you to do is write down symbolically that represents what you've seen and your understanding of what's going on a microscopic level. All right? So go through the PowerPoints, read the examples, click on the links. They're kind of fun. All right? All right. So I'm going to go to types of reactions over here. There's 5 basic types of chemical reactions. And you will have to, on the first exam, classify reactions as to one of these 5 types. The first type is combination. Biologists, they like their own word, synthesis. There is decomposition. There's single replacement. Also known as redox reactions. There's double replacement. And then there's combustion. So there's the 5 types of chemical reactions that we're going to start talking about. Now, each of these is a little bit different. Double replacement, also known as metathesis. Generally, the terms I put in parentheses are terms that are a little more old school. However, some of you are going to be taking the MCAT, the PCAT, the GRE, these high-stakes assessment exams, and you may have a test author that uses the old school terms. So I want you to be familiar with combination and redox and metathesis, because you go, whoa, this is a metathesis reaction? That looks like a double replacement to me, right? Okay. I've also heard them called single displacement or double displacement. So sometimes it's displacement, depending on the author, all right? Okay. First one we're going to talk about is combination. And it's just as you might think. It's when you take 2 smaller things
and somehow there's a chemical reaction that goes on and makes one combined thing. So those are fairly easy to figure out. If you got more stuff on the reactant side than you got on the product side, then your chances are pretty good it might be a combination reaction. A good example of a combination reaction is if you've ever burned steel wool. Anybody ever been here in Boy Scouts or Girl Scouts and burned steel wool? It's kind of cool. If you've ever taken steel wool and burned it, what you can do is you take a hunk of it. And what's steel wool made out of? Don't say steel. What's the element that it's made out of? It's iron. Good old iron. Iron rusts rapidly. It also burns very easily because it is very prone to oxidation. That's what iron is all about. So you take a hunk of steel wool, and I could put it on a balance, and I would look at the digital display, and it might weigh 1.97 grams. All right, I'm taking the steel wool off of my balance. I'm going to put it in a evaporating dish. I'm going to burn it. Now, when you burn steel wool, there's a couple ways you could do it. You could start with a Bunsen burner and put it on the edge. I used to do this as a demonstration in class, but because we don't have running water in here and we have carpet, I cannot do demonstrations in here anymore, sorry. Anyways, you take steel wool, you take a Bunsen burner, you can light the end of it, you turn the Bunsen burner off and you can blow on it, and it will burn the steel wool all the way through. It's actually pretty cool. Or you could take a 9-volt battery. You know the little 9-volt batteries that you put in your fire alarms? And the reason you need a 9-volt battery is because the cathode and the anode are on the same side of the battery. And what you do is you take, and if you're ever on Survivor, this is a skill you can use to start a fire with a 9-volt battery and a hunk of steel wool. You take the ends of the 9-volt battery, because it's the positive and the negative, you stick it on the steel wool because it is iron, it conducts electricity very well, and it conducts it so well, it heats up and starts on fire. How cool is that? All right, so now you know a skill. If you're out stranded somewhere, you can make a fire. Anyways, after we burn the steel wool, if you've ever seen steel wool burn, it doesn't change its shape a whole lot. It just sort of burns as an ember all the way through, and then it changes color. Originally, before you burn it, it's sort of blackish gray, and then when you burn it, it's kind of like a little less blackish gray and more earth-toned and silvery, and you get little balls of iron where it has kind of melted really hot. And if you touch it, it's real fragile. You know what steel wool is like when you touch it. It's kind of spongy. After you've combusted steel wool, if you touch it, it kind of crumbles, right? So if I took that steel wool and I weighed it after I burned it, what do you think would happen to the mass of the steel wool? Would it go up? Would it go down? Or would it not change? We're going to take a little vote. How many people think the mass would go up? Nobody. How many people think the mass would stay the same? A few. How many people think the mass would go down? All right, nobody's right. Actually, the mass goes up a smidge, believe it or not. And this is true of some things, because what you did is you rusted that steel wool very rapidly. All that combustion is rapid oxidation, which is a single replacement reaction. And what you did was you took iron as a solid, and what must have been added to the iron, since we're talking about combination reactions, and we had iron, what must have been added? Oxygen gas, absolutely. So now we've got a solid, right, because it started as a solid. We've got oxygen gas in the atmosphere. If you had your nomenclature in your back pocket, which you don't at this point, iron makes two kinds of ions. Ferric and ferrous, that used to be the old school terms for those two types of ions. They're either +2 or +3. We'll do both, +2 and +3. All right. If iron was +2 and it hooked up with oxygen in a combination reaction, making iron oxide, which is what rust is iron oxide, right? It made iron oxide. If we know that iron is +2, what's the ionic charge for oxygen when it's an ion? -2, very good. Now, if I was going to make a formula for iron oxide based on the +2 -2, what would the formula for the iron oxide be?
FeO2.
Well, everybody thinks it might. Well, first of all, why is that wrong? Oh, I'm sorry. Whoopsie.
Fe2, probably got all two.
Because the charge is linked on
We're not in the names yet, but yes, you're right. Thank you. I'm sorry. Somebody else said it.
the charges will balance out.
Well, this is not the lowest whole number ratio. Ionic compounds have to be the lowest whole number ratio for atoms in the compound. And if it's a 2 to 2 ratio, that's not the lowest whole number ratio. What's the lowest whole number ratio? 1 to 1, so it should be just FeO. What's feo in Spanish? Ugly. Iron all rusted, is it kind of ugly? I think it's kind of pretty. If you've ever seen a rusty nail, they actually get heavier. If you look at a rusty nail next time, it's actually bigger and fatter and takes up more volume than a non-rusty nail, and it's mostly on the outside. Why is it mostly on the outside? Because that's where the oxygen can come into contact with it and the chemical reaction can occur. Why does iron rust so much faster in water? What's that? Well, it's H2O, but there's plenty of oxygen in our air. It's touching it. It's touching it. The water's touching it, so the oxygen can get right to it and start doing its little redox reactions. If it's in the air, you know, the air has to come and a molecule has to hit it with enough energy and at the right orientation in order to react with the iron. But if it's in water, the water's all touching it and it can react fairly easily. All right, so let's balance our two equations here. You know what? I'm going to start on a new page because I made some work here. Oh, let's do the other one. So this would be if it was plus 2. If it was plus 3, what would be the formula for Fe, for FeO iron? All right, so here it would be hopefully you can all see that. I'm going to scratch this up so it doesn't confuse you. All right, now those equations do not follow the law of conservation of mass yet. They're not balanced. So what can we do to balance them? Now keeping in mind, nomenclature is hard and fast rules. You cannot change the subscripts to balance equations. You've got to only change coefficients, which are the numbers in front. Yes, sweetie?
I was just saying coefficients.
Coefficients only, right? You must have had the nomenclature, or you must have had chemistry pretty recently. You all good? Good. All right, so we got to do coefficients. So right off the bat, it looks like we got an issue with oxygen here. So what should I do?
Add it to FeO.
Here?
No, on the
As a coefficient, right. Okay, so that means now we have 2 pieces of FeO being produced. You can't change the nomenclature to adjust and balance your equation. So now the oxygens are okay, but now our iron is messed up. So what should I do? Add a 2. Oh, and what state of matter do you think that the iron oxide would be? Solid, most likely. All right, the second one. What should I do to fix this one? Usually what I do is I try to save oxygen for last. Oxygen is one of those that often appears in multiple parts of chemical equations, and I like to balance everything else first and then save hydrogen and oxygen for last. So if we did that, what should I do first to this equation? Got 2 there, so I have 2 pieces of iron now reacting with 1 molecule of oxygen. And what else should I do? I've got 3 oxygens here and 2 there. That presents a problem. When you got 3 on one side and 2 on the other, what's the lowest whole number ratio between 3 and 2? 6. How could I get 6 on both sides?
You add 2.
A 3 there, and then a 2 there. But then I got to change this 2 to a 4. All right, you guys know balancing equations. I'm not teaching you anything you don't know, right? It's just like a little bit of algebra trickery, isn't it? Balancing equations. So if you looked at this, you would have 2 pieces of iron, right? 2 atoms of iron. 1 molecule of oxygen gas would produce 2 of these FeOs. We'll have O be the open one. So that's the microscopic idea. All right, the second type of reaction is decomposition. The reaction I like to use for decomposition is this stuff right here. Anybody know what the common name of H2O2 is? Hydrogen peroxide. That's not the IUPAC name. If you had the IUPAC name, what would the IUPAC name? International Union of Pure and Applied Chemistry is the rules that is worldwide. It would be what? Very good, dihydrogen dioxide. So hydrogen peroxide is the common name, like water, right? Water is the common name for that stuff. What's the IUPAC name for that stuff? Dihydrogen monoxide, right? Did your lab teacher tell you a joke about the dihydrogen monoxide?
What's the joke?
Kills a lot of people.
It does, yes.
Yeah.
Back in the 70s when I was in school, some crazy grad students at Cal Berkeley, I think it was, started passing around a petition to ban dihydrogen monoxide. Sounds like a bad chemical, doesn't it? Want to ban dihydrogen monoxide. Some of them were responsible for hundreds of drownings every year. Primary component of swelling in the brain during encephalitis, right? That's water on the brain. So we want to ban dihydrogen monoxide, and they're passing around petitions to ban the dihydrogen monoxide. But you guys know better than that. All right, so decomposition of hydrogen peroxide. When I was a kid, my brother and I used to do a lot of skating. My brother had a skateboard and I had roller skates. And of course, back then they were the metal wheels. They weren't the nice plastic ones like you guys have now. And on these metal wheels, if you hit a rock, immediately you went down, immediately. So we used to sweep the whole driveway and stuff so that we could skate and not have these rocks. Well, you know, of course you always fall down. My mom would come in and my mom would go, oh, you fell down, you know, your knees would be all scraped up and you got strawberries on both knees. And she'd take the hydrogen peroxide and she'd pour it on the knee, both the knees. Of course, brother and I would scream. She's like, it doesn't hurt. I'll pour alcohol and then we'll see you scream. Right? So she'd pour her hydrogen peroxide, and what, if you've ever done that, or if you've ever seen that, what do you observe? Bubbles coming up. So it's changing from H2O2 and it's making some gas. So just like in the previous example, we used color or the emission of smoke to indicate a chemical reaction. In this case, when you see bubbles, that's often a chemical reaction, like Alka-Seltzer or what's the other one the denture stuff? Polydent. Alka-Seltzer generates, do you know what kind of gas Alka-Seltzer generates? I believe it's carbon dioxide. It's like the bubbles in a soda pop, and that's what makes your tummy feel better, is the carbon dioxide. The denture stuff makes bubbles of oxygen because the oxygen helps clean the dentures. And I only know this because I used to make lab kits that we had to send home to students, and we had to figure out ways for them to generate gases at home. And if they went and got Polydent and Alka-Seltzer, there you go. You got two kinds of gas you can generate. And we actually would use the oxygen gas to do stuff, which was kind of cool. All right, so if we decompose this stuff, like my mom used to, and pour it on her knees, and it all bubbles, what's it gonna decompose into, you suppose? If you see bubbles, you got some hydrogen. Wait, let me think. Nope, it's not hydrogen gas. That would be dangerous. It's actually oxygen gas and water. And we put water here as a liquid because as a product of a chemical reaction, it is a pure substance. Now, this would be an aqueous solution, so our surrounding molecules are not being depicted in the chemical reaction. I think that was a question a little bit earlier. How would I balance this? This is kind of a tricky one to balance.
You got a 3 H2O2.
A 3 here. Why would I put a 3 here?
At the beginning.
Oh, at the beginning. A 3 here?
Yeah.
3. All right, we'll try that. So that's 3 times 2 is 6 hydrogen. So what would I do here?
Could be.
Try 3. Okay.
Yeah,
3 times 2 is 6 oxygen. 3, 4, 5. No, 3's not going to work. Let's try something else. In these kind of problems, I generally save oxygen when it's by itself for the very last, because that's a good way to balance out the oxygen once you get everything else done. If you look at the hydrogens, well, that didn't help much, did it? Because they're both 2 to 2 there. But now I've got 2 oxygens here, 2, 3 over here. So I think your idea of getting 6 of them was probably a good idea, but we can do it in a different way.
Can you do 2?
2 here.
Yeah.
All right, so 2 times 2 is 4 hydrogen, so then I need a 2 here. I think that might work. 2 times 2 is 4 hydrogen. 2 times 2 is 4 oxygen, 2, 3, 4 oxygen. So we're good. Everybody see how that works? This equation now follows the law of conservation of mass, because it's balanced. On this one, I used to take this as a demo, and I would fill it with hydrogen peroxide, and I would put in just a hunk of anything organic. Meat, a vegetable, hunk of sugar, anything, and it just starts making all these bubbles that come up. The oxygen bubbles are coming up. When you buy hydrogen peroxide in the in the drugstore, what color is the bottle? It's a brown bottle. I suppose it's brown. Sunlight, well, this chemical reaction is catalyzed. What does that mean, catalyzed? Generally it means sped up. You can slow down chemical reactions and you still call them catalyzed, but you're just changing the rate at which they happen. Generally we're more used to thinking about them speeding up. These are what we call photo catalyzed, which means light will help catalyze this particular reaction, meaning make it go more in that direction, make it go to oxygen and water. So if they didn't have brown bottles, if they just had the clear bottles like they have for isopropyl alcohol or something like that, what would you be getting a bottle of? Some bubbly water, right? You don't want a bottle of bubbly water, right? You want a bottle of hydrogen peroxide, so that's why they put in the brown bottles. Well, the stuff you buy at the drugstore is about 3% hydrogen peroxide. It's pretty wimpy. In the lab, we have 30%, which is almost pure. It's super toxic. You get the stuff on your skin, it will start irritating and corroding and burning your skin right away. It's so toxic. In the bottles that we store this stuff in the lab, they're the funniest things. They have this little accordion thing. They look like this. And what happens is, over time, the bottle gets big. So the lab tech will come in, she'll unscrew the top, smoosh it down like an accordion, screw the top back in, put it back on the shelf. And then over time it grows up, right? Unscrew the lid, push it back down. What's happening here? Gas being produced, there's oxygen gas. That's the decomposition of the hydrogen peroxide that's happening. All right.
97% then.
What's that, hon?
And you said peroxide's about 3%?
Right, the stuff you buy at the grocery store, so it's 97% water. So it happens in an aqueous solution. But 3% is enough because hydrogen peroxide is pretty darn corrosive, and so you want to be super careful with that. All right, the single replacement, I thought I had given you guys a copy of the solubility rules, but that's okay. We've got single replacement rules, and we can use those right off the bat. Oh, and I didn't give you the general form of decomposition reactions. Oopsie, bad teacher. So general form, right? Like, I taught algebra for many, many years. That was awful. What's the general form for slope of a line? Y equals mx plus b. All right, this is the general form of a decomposition reaction. You take something big and you're breaking it up, right? So that's how you tell it. Okay, so now we need additional resources. And the additional resource we need is the activity series, which I did hand out to you guys today. This is a depiction of a whole lot of metals, and it does include hydrogen. Hydrogen's up there, isn't it? Yes, okay. Hydrogen's the only one that's not a metal, and hydrogen has a special place on the activity series. And it tells you which elements are most likely to react. Okay? So if you look at the arrow says ease of oxidation. And that's what a single replacement reaction is. It is a redox reaction. Okay, so you're talking about the ease of oxidation. And oxidation occurs when oxygen bonds to metal. All metals will oxidize. I heard somebody say in the grocery store the other day, oh, aluminum doesn't oxidize. Actually, it does. The reason the aluminum foil that you buy at the grocery store doesn't oxidize in your drawer or while you're cooking is because it has a very thin coating on it to keep it from oxidizing, because we would prefer to have nice shiny aluminum rather than kind of blackish aluminum if it's all oxidized. So all metals oxidize. It just depends on what is happening to them and what you have to do to get them to oxidize. Some are really easy, like iron. Where's iron on this? Oh, iron's right smack dab in the middle. Well, we've all seen iron oxidize, right? And these are actually oxidation reactions, where you're taking an element like aluminum that has all the electrons it was born with, and you're turning it into an aluminum ion, and you're setting 3 electrons free, right? Iron, solid, sometimes it forms a +2 ion, and it releases 2 electrons. So these single replacement reactions happen because one substance releases electrons, but then what must happen to those electrons? Somebody else takes some. And that's what redox means, is it's chemistry slang for oxidation, reduction. Oxidation, reduction is redox. So oxidation, and here's a good way to remember who is who. I like this one. Anybody ever seen this mnemonic device before? Oil rig. What does that mean? Does anybody remember this mnemonic device? Oxidation is the loss, right? And so reduction is the gain. All right. You can't have gain without somebody losing. So oxidation is the loss, reduction is the gain. That's the direction of electron transfer in an oxidation reduction reaction. So if you look at something like, you want to write a reaction for them, you can say Fe solid changes into an ion of iron. Generally that happens in aqueous solution, plus 2 electrons that you set free. You can also say the opposite is true. You can say oxygen as a, oh boy, it'd probably be a gas. You can hook up, let's see, 1, 2, 3, 4, how many electrons? No, it's probably here. That's not a good example. All right. If you're looking in a beaker, and you will be, this week is the nomenclature lab, and I think you have single replacement lab first, don't you, before you have double replacement lab? You guys probably don't remember. All right, if you were looking in a beaker and you took an aqueous solution, and before we can even talk about redox reactions, we have to talk about what happens in an aqueous solution. When you dissolve an ionic compound on an aqueous solution, the compound comes apart, it dissociates. So for example, if I put good old NaCl into this aqueous solution, there's a couple of good videos that I have that depict this on an animation perspective, which are really good and way better than what I can do. I'm going to make a bigger picture here. All right, we've got our aqueous solution. This is plain old H2O. And in, I'm going to drop some NaCl. Right? NaCl is good old table salt, common name. What's the IUPAC name for this stuff? Sodium chloride. All right. Sodium chloride, because it's an ionic compound, is a continual structure of repeating sodium and chlorine pieces. So they're all connected with a 1-to-1 ratio, and we call the lowest whole number ratio the empirical formula. So there's a whole bunch of NAs and a whole bunch of CLs, but ultimately in the end the ratio of the NA to CL is a 1-to-1 ratio. When you put this stuff in water, so I'm going to pretend I just put my crystal into water here, what happens is water molecules are very polar. Hopefully you remember this from Chem 130 or your high school chem. Water molecules, remember, are H2O. And the hydrogens are down on one side generally, and the O is a much bigger molecule. Because we have non-bonded pairs of electrons there on the water molecule, it makes this side of the molecule negative and this side of the molecule positive. So we call it a polar molecule. Water is very polar, and that's why they call water the universal solvent, because it is so polar, it can rip apart the sodium and the chlorine from each other. Now, when an ionic bond happens, sodium gives up an electron, it becomes positively charged, and chlorine becomes negatively charged. That's the nature of ionic bonds, is an electron is transferred from one element to another. What holds this whole thing together is the fact that they're attracted to each other now because one is positive and one is negative. Right? We got a positively charged particle here hooked up to a negatively charged particle, and that's what keeps the bond together. Was water molecules come up to the end, the outside of the salt crystal. If you've ever dissolved salt in water, especially like if you have that ice cream salt with the big chunks of crystals, you pour it in water, you'll notice that each crystal appears to just get smaller and smaller and smaller until it ultimately disappears. And what's happening there is the water molecules, they'll approach sodium, and they will turn towards sodium so that the positive end is away from sodium and the negative end is towards sodium, because of course opposites attract. Now, one water molecule is not going to have enough force to pull that ion off of the crystal, but the water molecules gang up on the ones, especially on the edges, or on the outside, and you can see that the way I'm depicting it, they all orient themselves. So the combined force of multiple water molecules is enough to break that bond right there and set sodium free. Okay? That first step is called dissociation. These are vocabulary words you need to use the rest of the semester. So you break the Na and the Cl up, and that's the responsibility of the water, right? The water goes in there, they gang up on the ions at the very edge of the crystal. They use their combined power to pull them off. Is that going to cost energy, or are you going to get energy back from that process? It's going to cost you energy, right? Okay, so actually if you measure the temperature of water, and then you put a bunch of salt in and you stir it around until the water dissolves the salt, what would you suppose happens to the temperature of the water? The temperature of the water actually goes down. Where's that energy going? Into breaking those bonds, right? So those water molecules, they use some of their latent heat energy to pull the crystals off of or pull the ions off of the original crystal. So the first step is dissociation. The second step is what we call hydration. And hydration means that the water molecules will now surround the sodium ion, once again with their little positive sides away from sodium and their negative side towards sodium. And the same thing happens to chlorine, but now when these polar water molecules approach chlorine, now the positive side of them are towards chlorine. So to the water molecules and drew them, now the positive side would be towards the chlorine, the hydrogen side would be towards chlorine. Same thing happens, they pull chlorine off during dissociation, and then hydration, the chlorine has a bunch of water molecules surrounding it, except now the hydrogens are towards the chlorine. So those are two super important processes that cost energy, right? And so the energy comes from the water, the temperature of the water actually goes down. This hydration ring also keeps the ions from recombining. Because what happens is they'll be moving around, and in a liquid solution, the ions and the molecules of water are always moving around, right? As they're moving around, they might bump into each other, and because the chlorine is negative and the sodium is positive, they are still attracted to each other. They want to get through and form a compound again because they're attracted to each other, but they cannot because of this hydration ring. How could I take the water and the salt and separate them? What would I do? I would just boil it, right? Or in Arizona, you could sit out in the summertime in June, right? Out on the sidewalk, and it'd be gone in a day. What would you find at the bottom of the container that you boiled the water from? You'd have some salt, and you could actually see the crystals. And the very cool thing about that is the crystals go exactly back into their cubic shape. So if you've ever done that, if you've ever evaporated salt from water, look at the little crystals. They're little tiny cubes, which I think is just amazing. There's a compound called copper sulfate that makes these really pretty diamond-shaped crystals. You dissolve it in water, you stir it up, you let it evaporate, it goes right back into the diamond shapes, which I just think is phenomenal. Because these are not organic substances. These are not things with a mind. It's the fact that the charges and the way that they orient when they combine to form a compound creates this idea of crystal structure, which we will also talk about in this class. All right, so this keeps them from recombining. So what happens if you take some of the water out? If you dehydrate it, you're taking some of the water out, then all of a sudden they can get at each other, right? They go, woohoo, I'm not hydrated anymore. All right, so that's what happens during the creation of an aqueous solution. So I want you to think about that from here on out. Whenever you see this symbol, what that means is generally what you have put into water was soluble. What does that mean, soluble? Okay, to the common man, they might say it dissolves because it appears to go away. But soluble to a chemist generally means that you're producing the ions. Now some things in this class we talk about it as a black or white bimodal situation, like they're either soluble or they're not soluble. When you get to Chem 152, there's varying degrees of insolubility, and you have to do a whole lot of math with the varying degrees of that. But in this class, we're just keeping it bimodal, soluble or not soluble. That means when you put this stuff into water, it will break up and form the ions that you're looking for, all right? So So that's what I want you to think about whenever you think about soluble and aqueous solutions, is you don't have that compound in water. You have the ions who have been dissociated, which made up that compound, and generally what that means is the ions that you have floating around in there are now ready to react, right? Because they're positively or negatively charged, and they're ready to react. All right, so for example, we're talking about redox. You're going to be doing labs with single replacement. For example, if we put CuCl2 solid into good old H2O, which is copper chloride. Copper chloride put into water. Copper chloride is soluble. What would the ions be that I would create in this particular solution of copper chloride? What ions would come apart from that? There would be copper ion with a +2 charge associated with it, and you determined that because you knew how. Chlorine is -1, and if there's 2 of them there, the copper has to balance that out to make the net charge of ionic compound 0. So -2 +2. So then what you would put, and I want you to think about this also, we're going to leave the water out because that's just confusing. When you have a compound like this, you get 1 piece of copper and 2 of the chloride ions. It is not this. A lot of students, when I tell at the beginning of the semester that there's 7 diatomic elements, they start at element 7, they make a figure 7 on the periodic table, they think, it's always going to be Cl2. No, it's not. When you ionize something and it is soluble, it does not make the gas. It makes ions in solution, right? So that's what you want. So we have copper ions and chloride ions. So in comes a hunk of aluminum. And you start seeing some fuzzy stuff growing on the outside of the aluminum, and you shake it off and it kind of filters to the bottom. You let it sit there for a little bit longer, more fuzzy stuff grows on it, and the fuzzy stuff oddly is copper colored. What do you suppose is going on in there? Well, you got a redox or a single replacement reaction. The general form of a single replacement reaction is you have something that is, there's 2 types actually. We'll probably get through both of them today. You have something that's a metal as a solid that you're starting with, plus, say CD is our aqueous solution, so that's generally going to be some sort of ionic compound. And since you see aqueous solution, that means you have ions of C and ions of D now floating around in your substance. If it's an ionic compound, is C going to be a metal or a non-metal? Metal. What's D going to be? Non-metal. So C is going to have what kind of a charge usually? Positive, and D would have a negative charge. Okay. So in a single replacement reaction, what happens is, I'm going to use the calculus if. Right? What's calculus if? If and only if A is more reactive than C, then a reaction will occur. All right, and then what happens is A replaces C. C now comes out of solution. It started as an ion. I'm going to show you some pictures of what this looks like in just a minute. It started as an ion in solution, remember, because it's an aqueous solution. Now C comes out as a solid. We are precipitating. This is called a precipitate. It's not like precipitation that comes out of the sky. Precipitate in chemistry is a solid that comes out of a solution. You're used to precipitation from the sky as rain coming out of the sky. No, precipitation in chemistry is a solid coming out of solution. You'll see it form. You'll see the stuff starting to appear. That's an indication of a chemical reaction. So then a reaction will occur. Well, okay, so let's see. In this reaction, we had aluminum and copper chloride. So let's make a reaction that looks like this. We've got aluminum is our solid, plus the copper chloride, whoopsie, which is an aqueous solution. Let's look here and see. Let's see, where is aluminum? Well, there's aluminum. Where's copper? There it is, there's copper. All right, so if this is ease of oxidation, so these are the most reactive. And these are the least reactive. All right, so is aluminum more reactive than copper?
Yes.
Will a reaction occur? Yes, it will. So what's going to be the products if it's going to look something like, oh, I didn't give you the rest of this equation, did I? C comes out, but then we get a new compound, AD is now in aqueous solution. All right, so based on that model, what would be the metal that comes out of this particular redox reaction? Copper. And that's why our precipitate was copper colored. That's what you would see in the beaker, right? Copper solid, what would go into aqueous solution? Aluminum chloride. Now we got to make new nomenclature for the product. And the charges change in redox reactions because there's electrons flying around. So let's look at aluminum and chlorine. What's the charge on aluminum always, always? +3. Good. What's the charge on chlorine? -1. So what's the nomenclature for aluminum chloride? 3. Now what would I put next to it? What symbol? AQ. All right. Very good. Let's balance this puppy. Aluminums look pretty good, but we've got problems with copper. It's the 2-3 problem again. So what can I do with a 2-3 problem? Lowest whole number ratio? 6 on each side. How can I make 6 here? A 2. How can I make 6 here? 3. Now that messes up my copper. So I put a 3 there. And my aluminum I can fix by putting a 2 there. All right. So now we're good. So now that's the symbolic representation of what's going on. I know it's hard to describe, but you are actually going to do a whole lab on this. My advice to you is save this great set of notes. And I will also post this video after class so that when you get to that lab and your teacher's going to ask you to write redox reactions, you're going to have a really good solid set of notes in which to do that. All right? I'm going to show you now what the microscopic perspective of redox reactions is because it's super fascinating. And it is basically the reason that batteries exist. Redox reactions. You know, redox reactions, modern society didn't figure out redox. Do you know who the earliest people that figured out redox reactions were? How to generate power in a solution. You can make a solution and you can put a light in it and you can make the light light up. The Egyptians, they made these solutions in these clay pots. And when they put their hands in the solution with some wires and stuff, they could feel the electricity going through, and they thought it was like some magical potion. So they used to put them in the tombs of the pharaohs, so that the pharaohs would have an energy source in the hereafter. So the Egyptians were the first ones that figured out what was going on in redox. Well, in redox, if we took a really big perspective of that reaction that we just talked about, here's our hunk of aluminum. Remember, we've got copper ions in there and chloride ions in there. And the chloride ions are not going to be particularly useful in doing anything. We call the chloride ions spectator ions. Because just like a spectator at a baseball game, they don't do much, they just kind of hang around and watch what's going on, right? What's important here is the aluminum and the copper, and the copper is a +2 ion. So copper will float up to aluminum, and because copper is deficient 2 electrons. How do I know it's deficient 2 electrons? It's got that +2 charge. Aluminum in its ground state as a solid metal, what do the charges of all ground state elements have? 0. So there's no charge there. So aluminum has all of the electrons it was born with. Well, because of the fact that aluminum is much more likely to give up its electrons than copper. When copper floats up next to aluminum, it goes, hey, aluminum, I'm missing some electrons. You got any spare? And aluminum says, sure, you can have some. And so there's actually an exchange of electrons. So copper comes up next to it. 2 electrons from aluminum come off of the aluminum atoms and go onto the copper. And so copper then grabs those 2 electrons and turns into copper solid. Well, as aluminum loses electrons, it then goes into aqueous solution. it makes +3 ions. So every time an atom of aluminum loses 3 electrons to the copper, it breaks off of that hunk of aluminum and goes into solution. So we're taking one metal that's a solid, putting it into solution. We're taking another metal that's in solution and making it a solid. Interesting thing about this particular reaction, anytime you have copper ions in solution, they give the solution a blue color. You will see that in lab. You will see a lot of blue color. I've seen this also in fish medicine. I used to have a tropical fish tank in my house. I don't anymore because it's too much work to keep them up. And tropical fish get this disease called ick. And what it is it's a parasite that goes on the side of their bodies, and it's white. And it doesn't kill them, but it's real irritating to them. And you'll see that they have ick because they sort of rub themselves on the gravels on the bottom, trying to rub the ick off of them. So I went to the pet store and I said, all right, what can I do? And they gave me this bottle of stuff. And I put it in, it turned the water all blue. I went, there's got to be copper. And I looked at it, and there was actually 2 kinds of copper in 2 different aqueous solutions. And apparently somehow it kills this fungus on fish. So when it's blue, it has copper ions. What we're doing here is we're taking the copper ions out of solution. So at the end of the reaction, do you think it would be more or less blue? Less blue. Because we're taking the copper ions out of solution. If we're taking them out of the solution slowly becomes less blue over time. And that's a visual indication. A permanent color change is a visual indication that a chemical reaction has occurred. All right? That's one that you can count on. So what's happening here is that original chemical reaction that we're going to use here is you had these things were in aqueous solution and these things ended up in aqueous solution. You have a metal and a metal. Now, when we're going to balance these, we have to write what's called net ionic equations. And this is going to be something that your lab teacher is going to ask you to do. So I'm going to start with this one here. And we're going to write net ionic equations out of this particular reaction. All right, that is our balanced equation. Now we're going to write our ionic equation. And then finally we're going to write our net ionic equation. The ionic equation still works in the symbolic mode, but now it's telling you a little more detailed about what's happening with the atoms and the ions in that particular reaction. And most single replacement reactions that we're going to be talking about in this class are going to be taking place in aqueous solution. All right. So what you have to say is you're going to say everything that's in aqueous solution, I have to show it as an ion in my ionic equation. If it's a solid or a pure liquid, it's not an ion, and you can leave it the way that it is. So we'll bring the 2 aluminums down as a solid because we still need those 2 aluminum atoms. But now, because this is an aqueous solution, and you know that during dissolution those atoms break up into their component ions, what I would have is if I had 3 of those copper chloride pieces, right? 3 coefficient means I have 3 pieces that each piece has 1 copper and 2 chlorides in it. If I broke up 3 of those things, how many ions of copper would I have? Wouldn't there be 3 copper ions with a +2 charge if I broke that hunk of stuff up, right? 3 of those. If I broke 3 of those up, how many chloride ions would I have? 6. See how that works? Does everybody see where the coefficients come from? Yes?
Which kind of reaction is
We're still on redox. We're still on single replacement. This one gets real deep. We may only get through this one today. All right, so there's the original reactants. Now I'm going to put the products. If it's a solid, a liquid, or a gas, it stays the same. Aqueous solution has to be ionized. So in this case, we're going to leave the solid just as it is. And we know that in your mind, wouldn't necessarily put this in your symbology, but in your mind, you know that the metals have no charge, right? 0 charge, because as solids, they have all the electrons they were born with. But now you've got 2 pieces of aluminum chloride. If I put 2 pieces of aluminum chloride in aqueous solution, how many aluminums would I get? 2. So plus 2 aluminums, each with a +3 charge. Ran out of paper there. Aqueous solution. Plus, what else would I have? 6 chloride ions also in aqueous solution. Now, here's how you know if you're doing this right, when you're writing ionic equations from your balanced equation, and yes, you're going to have to do this on the next exam and probably on the homework. If it balances here as a balanced equation, it should also balance as your ionic equation. Let's check that. 2 aluminums, 2 aluminums, 3 coppers, 3 coppers, 6 chlorines, 6 chlorines. Now, they change from atoms to ions or ions to atoms, and that's okay. It's just the basic number of things has to be the same, right? All right, I'm going to rewrite this in landscape version. Oh, you know, that screen is not going to show landscape version very well. All right, well, how about I write it smaller and I can get it in there because I want to show it all as 1. Uh-oh, plus 6Cl. You know what, let me give it. This might be a better way to do it because that's going to take some more room. All right, I think that's going to be better. Yeah, I hate that. So, what did I do with my ionic equation? Well, I'll just rewrite it. All right, so now we've got the whole equation there. Now we're going to look at the redox portion of it. What are the spectator ions here? What's not changing and not doing anything? Okay, those are our spectator ions. Right. Because aluminum is changing. How is aluminum changing? Well, solid to a liquid, but what else? It's going from 0 charge, right? It's becoming ionized. So it's going from 0 charge as a solid to having a +3 charge in aqueous solution. What's copper doing? The opposite. It's going from an ion in solution to being 0 charge as a solid. So now what we have to do is we have to show the redox, and these are called redox half reactions. So you're going to make a little box from aluminum, and then you're going to do the same thing for copper. Right? I'll show how they change. I'll even do them in different colors. All right, so now we're going to write the stuff that is aluminum in this top box. We're going to talk about, this arrow is going to show how aluminum is changing. So we'll use the black for aluminum and we'll use the purple for copper. So we're going to write down first 2 aluminums. Right, that's how it starts out. We're going to ignore the spectator ions and we're just going to put on the product side what we know happened to aluminum. So in this case, we had 2 aluminum atoms that became 2 aluminum ions that have a +3 charge. All right, look at the other part, the copper. We'll start with the copper. 3 copper ions, aqueous solution, changed into 3 copper atoms in solid state. That's the basics of what we happen. Now we have to add what, what electrons we're moving back and forth. Let's try the top one first. If I had a single piece of aluminum and I wanted to make it an ion, what would the atom of aluminum have to do to become an ion of aluminum? Have to lose 3 electrons. If I have 2 of those atoms, each of which must lose 3 electrons, how many total electrons would be lost? 6. So that's what you put. Did everybody see how I got 6 electrons? That's super crucial to this class. And when you get into 152, fully 20% of the course is going to depend on you understanding this. Yes?
So if it's losing electrons, how come it's +16 instead of -16?
No. Does that look like a minus sign to you here?
No, I asked, you said plus, and I asked if we're losing electrons, how come we have plus?
Okay, okay, I get your question now. Elements start out with all their electrons. We wanted to depict them as an ion and the amount of electrons they have released.
Oh,
Okay, they release that quantity as a result of 2 of those atoms going through. Now, is that oxidation or reduction?
Oxidation, reduction.
the mnemonic device up here so we can use this. It's oxidation. So if you forget on a test, just write oil rig on your test and make your teacher happy, right? So that is the oxidation. And you will have to know that. You will have to know how to write these equations. All right, now let's look at copper. Get my purple pen out for copper. All right, we'll look at copper ion becoming a copper atom. What did the copper ion have to do to become a copper atom? Had to gain how many? 2 electrons. If there's 3 copper atoms, each of which gains 2 electrons, how many total are gained? 6. Now we're going to put them on this side of the equation. And why am I going to put them on that side of the equation? Because this was how it started. It gained those electrons, where did those electrons come from? From the aluminum. It's a beautiful thing, this redox thing. How amazing is that? That's what goes on when junk rusts. Right? You ever watch that show? What is it? Cash Cab. Cash Cab, you ever watch that show? My sons and I, after my oldest one graduated high school, boy, that was a long time ago. That was about 8 or 9 years ago. I said, all right, you guys pick where you want to go. And I thought, France, go to Spain, someplace awesome. They want to go to New York City. Really? All right, so I went to New York City. I said, all right, at least if we see in New York City, we could maybe hail a cash cab and win some money. So we're always looking out for cash cab. So I used to watch that show. Is it even on anymore? I don't even know if it's on anymore. Anyways, well, one of the ideas of cash cabs, they ask you questions and you earn money. Instead of paying the cab, you earn money, and if you get 3 strikes, then they throw you out on the street. That's basically the premise of cash cab. One of the questions of cash cab was, what is the common name for the oxide of iron? What is the common name for the oxide of iron? Rust. They didn't know it. So they pulled over and they did the call out to a friend thing. Hey, the pedestrian comes by. Hey, what's the common name for the oxide of iron? Rust. No, didn't know it. So if you're ever on Cash Cab or game show, you will now know the appropriate response for what is the common name for the oxide of iron. All metals oxidized. One thing to also check, these equations should be balanced, and the electrons you lose should be equal to the electrons you gain. Yes?
Question about that. If you were to switch sides on that, like on the bottom on there, to put like minus 6 electrons, if you
Because that implies that, no, can't do that. One thing that chemistry is pretty specific. If you put the minus electrons over there, it almost implies that the reaction is going on that side, which is not the case, and you want to depict it like this. So you have to have the electrons being lost in the oxidation process, which means they're going to be on the product side, and you have to add the electrons being gained on the reduction process, and that's on the product side. And when you get into electrochemistry in Chem 152, you can change the direction of those with a simple electrical current. And that's the premise of all batteries, especially like the rechargeable ones. You just reverse the reaction and add the electrons instead of taking them off, and that recharges the battery. So we really actually have to be pretty specific on this one. All right, so that's, yes?
I'm still completely lost on how you got the 6 electrons. Does that have anything to do with the spectator ions, or no?
No, the spectator ions mean nothing. That's a good question.
Okay.
Let's go through the electrons again. If we just looked at, before I added those 6 electrons, all we had for this part of the half reaction, these are called redox half reactions. Let me make sure that we give you those vocabulary terms. This is a skill. You are expected to know when you walk into Chem 152. They expect you to know how to write redox half reactions. That's why we spend a whole week in lab doing this. And you could be writing lots of redox half reactions, I'm sure, with your lab teacher. Okay? All right, so redox half reactions, when you're looking at the electrons, and that is sometimes confusing. If you look at just what we had, remember what we started, we said there was only aluminum here, and we took the aluminum over here, and we didn't add the electrons. I like to look at the single piece of aluminum. This is our ground state aluminum because it's solid. That means it has all the electrons that it was born with, right? This is the ion of aluminum, which means with a +3 charge, it's deficient 3 electrons. So what did this aluminum atom have to do to become that aluminum ion? Had to lose 3 electrons. So a single piece of aluminum has to lose 3 electrons, and it loses them all at once. It doesn't lose them one at a time. It has to lose all 3 electrons in order to become an aluminum ion. But if I had 2 pieces of aluminum, each of which will lose 3 electrons, how many total electrons will I lose?
6. Because it's 2.
Yep. Okay. Same thing as reverse. Let's look at the reverse version. This is the thing that I added. If we look at copper here, copper started as an ion. It became a solid, which means it gained some electrons. If each copper here is deficient 2 electrons, what did it have to do to become a copper atom? Had to gain 2 electrons, right? But if there's 3 pieces of copper, each of which gains 2 electrons, then what's the total number of electrons that are gained? 6 total electrons are gained. Good question. That's often confusing. And these redox half reactions are confusing too. This is the battery industry. This is what these reactions are based on. Yes, hon?
I understand that part is the oxidation and the reduction. When you just put the label of reduction, I was like, well, reduction. So
Because it's this, the oil rig thing. Oxidation is the loss. Reduction is the gain. All right, if you look here, and that's another reason that we have to put it as not minus something. Here, we've got the electrons on the product side, so that means it was the loss, so that might be a good way to remember. Electrons on product side. And the gain, the electrons are on the reactant side.
well, why would you put -6 electrons to the aluminum and if it's losing?
That was my question. It's on the,
Because you have to show what it started out with. I don't know if there's any chemical equation that is a minus anything. We don't generally depict things. That's algebra. I think algebras get in the way
Okay.
here. And so we only have to say this is the thing that started out with, and we broke it up, and we broke it up into these pieces. Putting minus something is difficult representation symbolically. I think your algebra training is getting in the way.
Usually don't use fractions.
Yeah. All right. So there you go. All right. Remind me that this is where we stop today because I still have to show you the kind of single replacement with metal and an acid. All right. We'll talk about metals and acid single replacement on Tuesday. Make sure you get your homework done this weekend with the nomenclature lab.